This video will work through Lesson 3 for Unit 1. It should cover pages 6 and 7 in your pre-calculus notes packet. The first part of this lesson will extend our knowledge of the unit circle to start to talk about coterminal angles that show up on the unit circle, but don't occur just within one revolution from 0 to 2 pi. Coterminal angles are angles with the same terminal side, meaning the angles end in the same spot around the circle. They just might have more revolutions, either in the positive or negative direction, than our typical unit circle values. The first problem that we'll look at is cosine of 4 pi. So I have an axis here that I'm going to label with some of the radian measures that we already know. First, 0 and 2 pi occur on the positive x-axis, and we know that pi occurs on the negative x-axis. That's also where 180 degrees is. So 4 pi, we need to think about where that will fall if we continue to revolve around. So starting at 0 and going a revolution of 2 pi gets us one circle. If we went another half revolution, we would be at 2 pi plus another pi, so that would be 3 pi as well over here, coterminal with pi, and then another half revolution would get us another pi. So 4 pi is coterminal with 0 and 2 pi. You may notice that we have a bit of a pattern forming. All of the even multiples of pi are going to fall over here with 0 pi, 2 pi, and 4 pi. Any of the odd multiples of pi will fall where 180 degrees is, at pi, 3 pi. We would also have 5 pi here. So I'm going to add just a few more values so that we can see a few of the other angles that might fall here. And then I also want you to think about if we were to move in the opposite direction. So all of these green values are showing what happens when we revolve counterclockwise, as the unit circle typically does. Let's think about what would happen if we revolved the other way. So here, starting at 0, going in the negative direction, we would also get negative pi, coterminal with pi, 3 pi, 5 pi, any of the other odds. And if we continued a full revolution, we would have negative 2 pi here with our evens, and we could continue on to negative 3 pi, and so forth and so on. With this information, we'll be able to easily answer the first 3 examples on this page. We just simply need to look, are we looking for an even multiple pi or an odd multiple of pi? So number 1 here, cosine of 4 pi, that's an even multiple. So that's going to be basically the same as saying what's the cosine of 2 pi. And we know the ordered pair over here with the evens is 1, 0, which makes the cosine value, always the x value on the unit circle, 1. So that's our answer for number 1. When we look at the second problem, and in this one we're looking at a negative angle and we're looking for a sine value, I can see that it's negative 5 pi, so it's one of the odd multiples of pi. Doesn't matter if it's in the positive or negative direction. So that means it'll end up over here where 180 degrees falls. Because the ordered pair there is negative 1, 0, and the sine value corresponds to the y-coordinate, then this answer is simply 0, sine of negative 5 pi. Number 3 gives us a really big number, but all we have to do, like the others, is decide is it even or odd. So 57,801 pi. That is an odd multiple of pi, so it falls over here with all these guys. It's also a sine value, so very similar to the one right above it. Its answer will also be 0. If you look at examples 4 and 5, these get a little bit trickier because they have a denominator other than 1, like examples 1, 2, and 3. But we're going to use the same kind of starting point that we did with those to figure out where these angles will fall. So I'm basically going to change each of the fractions that we're looking at into mixed numbers. And once I look at their mixed number, I can use this even and odd pattern that we constructed up at the top and then just kind of tack on the remaining fraction to see where something like 17 pi over 6 will fall. So when I'm looking at that fraction, I'm going to just kind of carry over my trig function here. I'm going to ask myself how many times 6 goes into 17. And I know that 6 goes into 17 2 whole times, so 2 pi times. And then 6 times 2 is 12. I need 5 more to get to 17. So the remaining value is 5 pi over 6. So that's basically kind of a mixed number form equivalent to 7 pi over 6. When I look at my axes, 2 pi just gets me one full revolution back to the positive x-axis. So now I just need to see where does 5 pi over 6 fall after that. So 5 pi over 6, that's a little less than 1. We know the pi over 6's sit closer to the x-axis. So 5 pi over 6 will land somewhere over here. And if I look at that triangle that's created, I can see that it has a shorter vertical distance than it does horizontal. So that's going to be the 1/2 value. And since I'm looking for the sine of that angle, that's the one that I want. So I'm not even going to bother completing the rest of the triangle. I know that the sine of 5 pi over 6 is 1/2. So the sine of 2 pi plus 5 pi over 6 will also be 1/2. And since 2 pi plus 5 pi over 6 is equivalent to 17 pi over 6, that is my final answer. The last one, admittedly, is much harder, and it's harder because we're dealing with a negative angle, and you're going to see that when we break up negative 23 pi over 4 into its mixed numbers like we did up here with number 4, we're going to land on an odd multiple. So I purposefully made this one a little bit difficult just so that you could see all of the different kinds of things that might come up. But we are going to start the same way. So I'm going to carry over my trig function. This is looking at tangent. I'm just going to go ahead and think about this as if it were a positive number and toss negatives in the front of it. So I know that 4 goes into 23 5 whole times. So I would get negative 5 pi as the kind of whole number component to this mixed number. And then so 4 goes into 23 5 whole times, and it would have 3 left over. So negative 3 pi over 4 is the fractional part of that mixed number. So when I'm looking at where this would fall, I know that I'm rotating counterclockwise. I would go negative 2 pi, around again would get me to negative 4 pi, negative 5 pi lands on the negative x-axis. And then I need to rotate an additional negative 3 pi over 4. So I need to think about how far 3 pi over 4 travels. I know that 3/4 pi will go through one entire quadrant and then halfway into the next. So let me kind of highlight that in a different color. This part of it is the negative 3 pi over 4. Traveling the same distance 3 pi over 4 would, but in the negative direction. The triangle that's created on the pi over 4s are the 45, 45, 90 triangles, or the isosceles triangles. So the side lengths are root 2 over 2 and root 2 over 2, both positive since I'm in the first quadrant. And tangent takes the sine value, the vertical distance, over the horizontal distance, the cosine value. Since those are the same, when I divide one by the other, I get 1. And again, it's positive since both of those values were positive. The next set of examples is asking us just to kind of go back and look at one revolution from 0 to 2 pi of the unit circle, so you don't need to be thinking about multiple revolutions for these examples. And it's really asking us to work backwards and figure out what angle or angles make this statement true. So you need to still be very familiar with the unit circle, and your answers now are going to be angles instead of your answers being side lengths. So this is typically how I break these down, and you can see that I've kind of sectioned off this page with these red lines just so that the problems don't run into one another. I like to draw axes for each of these problems so that I can think about what quadrants I'm going to be working in. And I start every problem the same way just by focusing on the quadrants. So when I look at any sine function that gives me an output of a positive value, I think about the fact that the sine represents the y coordinates on the unit circle. So because this 1/2 is positive, I need to know where are the y values positive, and that's going to occur in the first and second quadrants. So my possible answers will show up in those two quadrants only. The next thing I'm going to do is think about what the triangles would look like that produce an answer of sine of some angle gives me 1/2. Since, again, sine is the y value, I'm looking for a shorter vertical distance than a horizontal distance. So I'm looking for the values that are a little bit closer to the x-axis. As we've discussed in class, those are the pi over 6's. So I know that that value in the first quadrant is 1 pi over 6. And I know the value in the second quadrant is 5 pi over 6. It's a little bit less than an entire pi. So my final answers are pi over 6, even though my drawing isn't great, pi over 6 and 5 pi over 6 for number 1. What that means is that if I took the sine of pi over 6, I would get 1/2, and if I took the sine of 5 pi over 6, I would also get 1/2. We'll apply the same thinking to number 2, but this time let's take a look at a different trig function and also some negative values. So we're looking at cosine for this one, which is going to focus on the x coordinates. Because the output is negative, I need to think about what two quadrants produce negative x's, and that's the second and the third quadrant. So I'm going to have different places where my triangles occur. This wants our x values to be the longer side of the triangle since it's root 3 over 2 as the value. So these are also going to be triangles that are longer than they are tall, but they're in different quadrants than the last one, or at least this second triangle here in the third quadrant is in a different location than our values for number 1. So still with our values closer to our angle measures, our terminal sides closer to the x-axis, these are the pi over 6's. I just need to pick the correct ones. So in the third quadrant, that value is 5 pi over 6. Again, a little bit less than a whole pi. And in the third quadrant, it's 1/6 more than a whole pi. So it's 7 pi over 6 as our final answer. The second two examples have one additional piece to them, which are going to narrow our quadrant choices down to just one quadrant instead of two. So if you notice, this piece here and this piece here, that's what's going to do that for us. So I'm still going to use some check marks thinking about the first part of the problem, and then I'm going to narrow down those two choices based on the second part. So here we go with number 3. A tangent value that's a negative. Well, I know that because tangent is constructed from sine and cosine, Both sine and cosine being positive in the first quadrant means tangent is positive in the first quadrant. And both sine and cosine being negative in the third quadrant means tangent is positive, since we take a negative divided by a negative. So tangent produces a negative result in the second and the fourth quadrants. Now I'm looking at this second piece of information that I've circled. So I want tangent not only to produce a negative, but I also want secant to produce a negative number. It says that secant is less than 0. Secant is the reciprocal of cosine, and reciprocals keep the same sign. So basically think about secant as cosine as an x value. When I look at these two quadrants, 2 and 4, that I've already checked off, the only one of those that produces negative cosine and therefore negative secant results is quadrant 2. So I know that I'll be working only in quadrant 2 for problem 3. What I need to think about next is what that triangle will look like. So tangent can be a little bit harder to think about since tangent is constructed with both sine and cosine. But if you've done enough unit circle practice, you should know that tangent producing either a positive or a negative 1 means that we're landing on one of the pi over 4 values, because the pi over 4s are the 45, 45, 90 triangles, where sine and cosine are the root 2 or over 2s, whether they be positive or negative. So in our second quadrant here, the terminal side of our angle will look like this, creating the 45, 45, 90 triangle that gives us negative root 2 over 2 for the x and positive root 2 over 2 for the y, which is again what creates that negative 1 for tangent. When I look specifically at what angle that represents, because it's in the second quadrant, alpha, so we're using just alpha, a different Greek letter instead of theta, alpha would be equal to 3 pi over 4. So that's the only answer here, because it gives us tangent of 3 pi over 4 is negative 1, and it guarantees that the secant of that angle is less than 0, mainly that it's meaning that it's negative. Last but not least on this screen, we'll look at number 4, sine of beta, another different Greek letter that we're using for our angle, so we're looking for what beta equals. Sine of beta is root 2 over 2. This is another example where we're going to be on one of the pi over 4s, because that's where the root 2 over 2's fall. And sine is a positive root 2 over 2. So similar to the first problem, that means we have to be in either the first or second quadrants. The second piece of information tells us that tangent also has to be positive. We know that tangent is always positive in the first quadrant. Everything's positive in the first quadrant. And we know that tangent would be negative in the second quadrant, because when we take sine, which is positive, over a negative cosine value, it will result in a negative number. So our answer here has to fall in the first quadrant. This one's kind of easy, because knowing that it's root 2 over 2 and the pi over 4s, beta would just be 1 pi over 4. So here we are moving on to page 7 of our notes and the last 4 examples for this video. Each of these will be a little bit different from the last. Number 1 on this page says that we are going to assume theta is an acute angle, so less than 90 degrees, in a right triangle satisfying the given conditions. We want to evaluate the remaining trig functions if cosine is 5 over 8. So that's really what the condition is. Cosine is 5 over 8. So you can see that I've already drawn a right triangle here. You should do the same. So I picked one of the corners to label theta. Doesn't matter which one you do as long as it's not the 90 degrees, since it has to be an acute angle. And then I'm going to use this fact, cosine of theta is 5 over 8, in order to label a couple of the side lengths. So cosine, we know, is adjacent over hypotenuse. so I can label the adjacent side to theta 5 and the hypotenuse 8. If I want to find the remaining trig functions, I'm going to need to know what that opposite side is. So I'm going to label it x. If we do the Pythagorean theorem, x squared plus 5 squared equals 8 squared. Solve, you'll get x equals root 39. That is our opposite side, and that will allow us to fill in the rest of the functions. Now, I kind of just like to list all 6 of them if I need to do this, and I like to list them next to their reciprocal values. So once I fill in sine, cosine, and tangent, I can just flip them all around in order to get cosecant, secant, and cotangent. So let's just start filling them in. We know that sine of theta is opposite over hypotenuse. Opposite of theta is root 39. Hypotenuse is 8. Root 39 can't be simplified or reduced any further, so I can just leave my answer like that. Cosine was already filled in because that was given to us in the original problem, so that's 5/8. Tangent of theta is opposite over adjacent. And then in the next column, I just take their reciprocals, so I flip them around. And what you want to make sure you don't forget to do is rationalize any of your final answers. So for example, this first one, when we multiply by root 39 over root 39, will give us a final answer of 8 root 39 over 39. For secant, I'll flip it to get 8/5. And cotangent will be 5 over root 39, and then rationalize in giving your final answer. And that's it for example 1. Example 2 is different for a couple of reasons. The first thing I'd like you to notice is that it doesn't just tell us that theta is an angle in a right triangle. It gives us some of the kind of qualifications that the problems on the last slide did. It gives us a value for tangent, and it tells us that sine of theta has to be positive. So that we're going to think through the quadrants the same way we did before. In fact, let's just get that out of the way. So I've drawn some axes here. I know that tangent is negative in the second and fourth quadrants, and I know that sine is positive only in the second quadrant between those two. It's positive in the first and second, and so the second quadrant is the overlap. So that's where I'm going to need to draw my triangle. Again, the first problem didn't really give me information to draw within a certain quadrant. I suppose we could have drawn only in the first and fourth, thinking about cosine being a positive value, but we didn't really need to do that because it didn't have this other qualification here that sine of theta has to be greater than 0. So anyways, I'm going to go ahead and draw a triangle in that quadrant, always coming from the origin and always with my 90 degrees touching the x-axis. What I want you to be careful of here is just because you have tangent doesn't mean you automatically have sine and cosine. Some people will look at this and say, well, tangent sine over cosine. So that means sine of theta has to be 4 and cosine has to be 3. Or maybe you would call one of them a negative. But that is not true. Just because tangent is 4/3 doesn't mean sine is 4 and cosine is 3. For example, just look at the problem above. Tangent was root 39 over 5, but sine wasn't root 39, cosine wasn't 5. They were something else that their ratio simplified to that. So don't make that mistake. What we want to do instead of that is just use the opposite and adjacent rules to label our triangle. So using tangent as opposite over adjacent, we know that opposite of theta is 4. We know that the adjacent side is 3, and really that's a negative 3, that being our horizontal distance, and if we're in the second quadrant, it has to be negative. The 4 is positive. The vertical distance will always be positive in the second quadrant. So when we see this, knowing that we need cosecant and cotangent, cosecant specifically will use the hypotenuse of this triangle. So the radius of the circle, you could call it x, you could call it r, you could call it any variable. You'll do the Pythagorean theorem again in order to find out what that value is. So you'll do 4 squared plus negative 3 squared equals r squared. You will get that the radius or the hypotenuse is 5. With that, you can fill in cosecant. So if cosecant is the reciprocal of sine, and sine is opposite over hypotenuse, cosecant is hypotenuse over opposite, so it is 5/4. And cotangent is just the reciprocal of tangent. So we could have answered that one before we did any of this work with the triangle, since we already knew what that tangent was, negative 4/3. That means cotangent has to be negative 3/4. And those are the only two trig functions we need to find based on those directions. These last two examples will feel more similar to number 2 than number 1 on the same page. What's different about them is that instead of giving us some existing trig function, it gives us an ordered pair in each of these to work with. So it's still going to be constructing a triangle, but you're using that ordered pair to do so. Thinking about number 3, we know that the terminal side of a central angle passes through the point 12, 4. Both of those values are positive, so that's in the first quadrant. We're going to have a triangle that goes over much further than it goes up. Don't worry about drawing these too accurately, but as always, theta sits near the origin and the 90 degrees sits on the x-axis. Since we went over 12, this is a distance of 12 in the horizontal direction. Up 4 means the vertical distance is 4. And similar to number 2, use the Pythagorean theorem to find the hypotenuse. You guys should be pretty good at the Pythagorean theorem by now. When you do the setup and start to crunch some of these numbers, you're going to get to r squared equals 160. When you take the square root, this root can be simplified. It is simplified to 4 root 10. We always want to use simplified radicals in our answers. I should mention, because I didn't last time in number 2, that the radius or the hypotenuse will always be a positive value regardless of what quadrant we are in. So you want to worry about the signs of the legs of your right triangle, but the radius is always a positive, which is why I didn't put plus or minus here when I did my square root. Okay, so we know what the radius is, and we needed that in order to find the answer that we're looking for. We're looking for just sine of theta in this one. Sine of theta, so we've got opposite is 4, hypotenuse is 4 root 10. The 4's can cancel, so I have 1 root 10, and then you're going to rationalize that to get your final answer of root 10 over 10. And make sure that your final answer has an appropriate sign. In the first quadrant, sign is positive, so we're in good shape. Last example for today, very similar to number 3. Sometimes I save the hardest example for last. In this case, I'm hoping you'll find that this is the easier example, so we'll end on a really happy note here. The terminal side of a central angle passes through the point 5, -5. So if I go over 5 and down 5, I am in the fourth quadrant. So positive 5 here, negative 5 here. Oops, that's where I would fall. Here's my 90 degrees, here's theta. We want to find the tangent of theta. Before you do the Pythagorean theorem, notice that we already have the information we need for tangent. Tangent requires the opposite and adjacent sides. We have those. So you can skip that middle step and just go right for your answer. Tangent of theta is negative 5 over 5, which is negative 1. And hopefully that makes sense. We do have an isosceles triangle here. The legs are the same length. Different signs, but the same length. And while this isn't a unit circle triangle, it is isosceles, so the 45, 45, 90 is really just kind of, the 45 degrees is kind of extended. So getting a tangent value of negative 1, which is something we know comes from our unit circle practice, shouldn't be surprising. That concludes this video. You should be in good shape to do assignment 3 posted on our course calendar. Good luck, and I'll see you next time.